Good morning, everybody, and welcome to Papalim Physics Classroom. Today we'll be doing a review on Tanjong Katong Girls School 2023 Science Physics Prelim paper. Okay, the paper that I'm using is available at my Google Drive. I have shared the link in my description in the link in the description panel below here. So if you are interested, you can go and download the paper and give it a try. Okay, the paper is actually a good paper with some interesting questions that I think is actually of interest to some of us. Okay, so this video will be a very, very long video. So if you are only interested in like maybe paper 2, section A, question 2, okay, please scroll ahead to that particular video and just take a look. Okay, don't watch from the start to the end. Okay, it's very long. Okay, so without delaying, okay, let's start. Let's look at the paper. Okay, I have actually outlined some of the interesting questions that you may want to take note. The question that's interesting to us is listed here. Question 3, 4, and question 11. For question 1, question 1 is a velocity time graph. It's a question on kinematics. As usual, okay, the question will involve looking at describing the motion of the car itself. So same as before. During description, remember, if I give you the velocity time graph, remember to describe one additional information, one step ahead. So if I'm giving you a VT graph, okay, you make sure that your description will actually covers acceleration. If I give you a displacement time graph, okay, if I give you a displacement time graph, make sure that when you describe this displacement time graph, you describe one step ahead, which is actually what I need is the information about the velocity of the object itself. Okay, so when you talk about description, there is a standard way of writing or standard way of describing. So it's always one step ahead of the graph that I given you. Okay, for first the 20 seconds, I would say it's quite straightforward. It's a constant velocity. But what I will actually include here to be safe is actually I will include the word zero acceleration. Okay, to make sure the answer is like bulletproof. Okay, so I always describe what is one additional information one step ahead. In addition, for the next 10 seconds, okay, other than writing the velocity decreases from 25 meters per second to 10 meters per second, I will actually give information about acceleration. So I actually will tell the marker that the car is actually moving at a constant deceleration. These are the information that I actually refer to when you describe the velocity time graph, you actually give additional information. Okay, not just regurgitate the whole graph pattern out. Okay, so same thing as before. Remember, okay, if I give you a velocity time graph, description will entails acceleration. If I give a displacement time graph, the description will actually entails velocity. Okay, so this is what I always remind myself to do when I do description question. For deceleration, 25 meters per second. I will not go through the question here because I would say it's quite fairly straightforward. But one thing to take note for all students is that if you are using the formula A equal to V minus U divided by delta T, okay, which is the initial final velocity minus initial velocity. Remember, this question only give us, or the answer for this formula, okay, it gives us acceleration. Right, so if you're looking for deceleration, what you're expecting to do is at the end of the day, for this answer, you will be expecting a negative sign. Okay, but this is acceleration. Okay, so if I want deceleration, remember to remove the negative sign to actually present it correctly. Okay, if I need a deceleration. For question C, distance traveled from 20 to 30 seconds. Remember, distance traveled at upper side now, okay, we don't just rely on distance equal to speed times time. What we rely heavily on is when I look at the distance move, am I actually looking at the area under the graph, okay, for VT graph. Okay, the area under the graph will actually give me one thing, which is the distance traveled. Okay, so the distance traveled in this case is actually what we call area under the graph for between 20 to 30 seconds. So 20 to 30 seconds, it will be this particular shape here, okay, which is the trapezium. Okay, or what we call a triangle plus a rectangle. Okay, so actually the question is asking for actually to find the area under this 20 to 30 seconds, which is this trapezium. So the area of the graph will be the distance traveled. Okay, so this is quite straightforward. For D, okay, the question mentioned is a deceleration for the next 20 seconds, decreasing deceleration. Okay, so what does it mean? Okay, deceleration, it will mean it's a negative gradient on the graph itself. If it's decreasing, means it's a decreasing negative gradient. Decreasing negative gradient means the graph is actually getting gentler and gentler. The gradient is negative sloping. Okay, negative sloping from top left to your bottom right. Okay, then after that, the gradient of the graph will be getting gentler and gentler and gentler. So that's why the line will be this. The answer will be the red color one. Yes, so that I'll make sure that the gradient of this graph, okay, is getting gentler and gentler and gentler and gentler. Okay, so just reminder, okay, velocity time graph, the gradient is actually the acceleration. Okay, so now they are looking at deceleration, which is meaning it's a negative acceleration. And the decreasing in front represents, okay, is a slope is getting gentler and gentler and gentler. Okay, and that's why the answer will be denoted by the red color marker here. Okay, question one, not difficult at all. Actually, it's quite straightforward. Now let's look at question two. Okay, question two we look at is the stationary vehicle with large wheels. Okay, stationary vehicle with large wheel, and we have a weight of 120 kilonewton. Okay, and the wheels are in contact. Okay, question 2A is quite interesting because they ask you to draw the forces that acting on the wheel of the vehicle. Okay, most of the time the question will ask you for the weight itself, ask you to draw the weight, which we always know is draw always through the CG of the object, label it as weight. But as of today, as of this question, okay, the question is looking not for the weight, it's actually for the contact area, where the force that act on the wheels. Okay, so if the car is actually resting, if the trailer is resting on the ground will exert the force onto the wheel. So the force will actually be upward force. So the upward force we are looking at is actually pointing upwards. Okay, in this case, this way. Right, remember, in this question here, because the way the picture is drawn, there's actually two wheels. So within the contact force you actually draw should actually be targeted at two wheels itself. The front two wheels, what you can see. And so don't just what we tend to do in the normal question that when I give you a box, okay, we tend to just write the normal reaction force, just draw it through the center here. Okay, so in this case, the marker won't accept any normal reaction force going through the center of gravity. Okay, so in this case, this particular question, if you write this, okay, this question here, this answer here will actually be marked wrong. Okay, so you must know what you're looking for. So the question is looking for normal contact area on the wheel itself. Okay, so it's upward force, but it's targeted at the wheel itself. So the location that we are looking at is actually the wheel itself. Okay, so these are the things that you have to be careful. Definition of center of gravity, I won't dwell too much on it. It's in the textbook, so I would say it's fairly straightforward. Pressure wise, for this question, area is given. The total area here is the total area that we are looking at is 0.15. So I wouldn't say it's actually not difficult at all. So it's force divided by area. The only thing that you may want to take note is that the question given is 120 kilonewton, so there's a prefix of kilo there. So you must remember to release the prefixes. So kilo will be 30 here. So it'll be 120,000 Newton divided by the area here, which is 0.15. Okay, so if you do the mathematics, the answer will actually come out quite straightforward. So for this question wise, for 2C, I would say it's fairly straightforward. The only thing you must be careful is the prefixes. Okay, so make sure the prefixes is actually accounted for. Okay, don't just leave the prefixes like you neglect the prefixes. Okay, so just take note of it. For question 3 is an interesting one. Okay, question 3, we are looking at two particular can. Okay, can A is dull, can A is dull and black. For this particular case is this. Okay, now the question part A asks, can B radiate heat at a slower rate? Okay, suggest a reason for this. Now, take note for this question, right? I would say the answer most of us we actually will know. Why? Because we know that we always like to say that can A is black. Okay, black is a good absorber or good emitter. So remember, first thing first is when you look at the writing, when you look at absorber and emitter, look at the context. Okay, the questions will either need this to be an emitter or it will be an absorber question. Remember, you must decide which is which. Okay, do not write both. You don't just blindly just write good emitter and absorber. Okay, if you write like that, most likely the marker will mark you wrong because you have not actually analyzed the context. In this question, because the water is hot, surrounding is actually cold. So actually heat will be actually transmitted in outward direction. So in this case, we are looking at the whether it can A or can B, they are acting as an emitter. So I only will accept emitter as one of the keywords. Now, in this case, the second thing that we need to take note is that the question is asking for can B. So your answer here should be targeted at can B to explain why can B is a bad emitter. Okay, so in this sense, I will actually only accept that because can be why it's shiny and white surfaces, and because it is a poor emitter. Okay, so if you look at the context of the keywords here, remember the question is asking for can be, so I need to give reasons pertaining to Chem B. Do not, okay, try not to answer by the reverse. Okay, try not answer by reversing. Example, the question asks for Chem B and you actually explain for Chem A. Chem A radiate faster because Chem A is a good emitter. But the question is asking for Chem B, not Chem A. So you are not answering the question. So I would say that if that's the case, the marker has the right not to give you the marks itself. So in exam, remember, students, we have to be concise and we have to be precise. Okay, know what the marker wants and know where are the answers and where are the keywords. For 2B, you find that the Chem A, Chem A, where Chem A is actually, the graph of Chem A is going down. And Chem A, you'll find that there's a T1, there's a plateau at T1, where the temperature will not drop below T1. I will say that the questions, for this answer, most of us will know that T1 will be what we know as the room temperature. So either you give me the surrounding temperature or what you call the room temperature. So the first keyword I'm looking at is that for the students to identify that it is actually T1 is actually the room temperature and or what we call the surrounding temperature. Second one I'm looking at is that whether the students can apply the keywords. When we say that the T1 is actually constant, okay, I'm not interested in students staying at constant because it's already on the graph. But what does the constant T1 means? So the additional information that I need to know is actually the students need to show me or need to write down the keywords such as thermal equilibrium. Is that the object Chem A actually reaches thermal equilibrium. So one of the keywords that I'm looking at when the students are writing is actually he or she will be able to write thermal equilibrium to be able to identify thermal equilibrium situations. If you don't want to write thermal equilibrium, the other way that I can write to replace thermal equilibrium is actually no net transfer, no net heat transfer. It's not no transfer. There is still transfer. Chem A is still giving out heat. Chem A is still absorbing heat from different directions. But just that the net gain and the net loss is actually the same. That's why we look at it as no net transfer, no net heat transfer. Okay. So if you're not looking at the word thermal equilibrium, I'm looking for the word no net heat transfer. You need to use the word net because net will imply the amount of heat gain and the amount of heat loss is actually the same. There are still heat gain, heat loss ongoing. Heat loss, heat gain is always ongoing one. The only time that it stops gaining heat or emitting heat is when the body is actually at 0 Kelvin, which is negative 273 degrees Celsius. Okay, so for normal temperature, every one of us will actually gain heat and lose heat. It's just the rate is different. In this case, because it's thermal equilibrium, it means that the heat gain and the heat loss and the heat gain will actually be the same. So whatever is gained from one side is actually equal to the other side. Okay, so take note of the keyword. Sketch the graph, okay, of Chem A without the lid. Okay, now without the lid, you must remember, without the lid means that there's room for evaporation, there's room for convection, hot gas will rise and cold air will sink. So there's actually more heat loss. So in fact, okay, the heat at each temperature, the water will actually, the heat loss will actually be much greater. So the heat will actually be reducing at a greater rate. So that's why for the first part of the graph, it's actually decreasing. It's actually shorter. But eventually, because they are in the same environment, they will still hit the same T1, which is what we call the room temperature. So without the lid, the heat loss will be faster, which is denoted by the first section, the yellow highlighted one. And eventually they will still, but eventually it will hit T1 again, but he will hit T1 earlier. Okay, and it will remain at T1 like for the rest of the whole journey because the Chem A has reaches thermal equilibrium. Okay, so just take note of the graphing. Right, part C, quite straightforward. This one I will not go through much. Okay, you should know already what are the users for all the components of the electromagnetic spectrums, what are the users and what are the advantage and disadvantage, and even what are the property of EM spectrum. Okay, these are the bread and butter that we need to know. For question 4, okay, question 4 is a heating, is a cooling curve, is a heating curve. Okay, one thing to take note is that the object starts with ice cube. Okay, so this is ice cube. Right, so it's an ice cube and it's actually gently heated up in the metal container. Now, stage W and WX, I would say it's quite straightforward. So this is solids. Okay, so if solids, you will go through melting first. So that's why WX is actually what we know as your melting phase. Okay, so melting phase, then followed by heating again, then followed by boiling. So these are the few stages that we are looking at. Now, state 1 differences between VW and XY. VW is here, heating. Okay, VW is here. Okay, then your VW is here, then VW is here, then followed by XY. Okay, so now this what we are looking at. We are looking at the two heating stages. Okay, so one obvious thing that we have to take note is the two stages they are heating, but actually they belong to two the medium that the particle that we're looking at, they are actually at two different states. For VW is straightforward, it's a solid state. I'm heating up the object, the ice cube. VXY is actually what we know as your liquid phase ready. So usually all the ice actually melted and it's all liquid. So XY is what we call heating, but it's at the liquid phase. Now, two differences between the particle, it's not between the stages. So you cannot give me like simple answer, say, oh, the VX is solids, XY is consists of pure or all the liquid. Okay, so this is not what the question is asking about. The question is asking about what is the difference between the particles. Okay, so particles, I will say it's quite straightforward, is that the particle, I'll give you three here. Okay, the marker has actually give three differences. One is pertaining to the orderly arrangement of solid and in disorderly arrangement of a liquid. The other one we look at is the arrangement also, but we look at the fixed position. Okay, solid, as we all know, is fixed position, but liquid is not. They are able to slide across each other. Then the third differences we look at is in terms of the strength of the intermolecular forces. Okay, remember to use the correct keyword, intermolecular forces. Don't write bonds, don't write forces. Okay, here the keywords here we use is actually quite specific. Okay, in here we are looking at intermolecular forces. Okay, the forces between the molecules. Okay, now, for part C. Okay, for part C, explain why it is dangerous if the container is sealed. Okay, I will say that on one look we will know that it's dangerous. Why? Because the can, if it's sealed, we might have experienced before, is that if you have a sealed can, if you heat it up, the can literally will explode one. Okay, but now the only difference is that I need to explain in terms of the gas particles, the motion of the gas particle. So we start from basic. Okay, when I start heating up, what happened to the gas particle in the container? Okay, so for gas particle, so you will gain EK and you will move faster. These two are what we know as the keyword, the energy pertaining to the kinetic energy, the energy in the kinetic store. Okay, so the kinetic energy will actually increase. And what does it entail? It entails that the particles are actually moving faster. So these two keywords are actually what we call tagging keywords. Every time you mention about EK, you mention about the velocity. So these are tagged together. After that, what happens is that when they move faster. Now take note, for these particular cases, the number of particles never increase. It's just that the same number of particles are actually moving faster. And move faster, what is the next outcome? It will be bombardment. The collision will be bombarding more frequently, more often. So you actually see more collision. So it's like a step by step. I move faster, I gain energy, I move faster. When I move faster, I collide more often. And when I collide more often, because of my increase in collisions, numbers of collisions, the force exerted on the wall is actually increases. Remember, here we are looking at the container exploding. So we are looking at the force exerted on the wall of the container, not on the particle itself. Okay, so because the molecules now travel faster, they collide the wall more often. So then after that, you will have the force exerted, the particle move faster, the particle gaining EK, the particle gaining EK and the particle moving faster. And after that, you have the more collisions. And eventually, what's the final outcome? Number 4, it will be larger force will be exerted onto the wall itself. And with larger force, it will mean that the pressure in the container actually increase and eventually it will explode. So if you look at the keywords, although it's actually 2 marks, but actually there is a few sets of keywords. Primarily, the first set will be the EK moving faster. This set is one set. Usually, every time we write about kinetic energy, we actually need to tag off with we need to end it off with the velocity. Second one is to tell me that it actually collide more often. The increase in the energy actually leads to more collisions. So more collisions one way. So this is more collision. Then after that, with more collisions, I actually has larger force exerted. And because there's a larger force, what happened is the larger force will actually cause pressure to build up. And when pressure build up, okay, the pressure will actually cause the container to explode. That's why it's bad for these particular cases. Okay, so you look at the keywords. We look at when we use kinetic particle model. okay, to answer the question. So the keywords you have to take note. Okay, 2 mark doesn't mean just 2 keywords. It's actually a series of keywords here. Question four is a mirror and a glass block situation. Okay, so I would say that it's fairly straightforward. It's just that for light ray, remember anything for light ray, you need to draw the normal, and the normal is always perpendicular to the surfaces. And with the normal, what I'm interested in is what is the incident angle and what is the refracted angle. So remember, the refracted angle and incident angle is always measured from the normal to the light ray itself. Okay, so like what I draw on the picture, so this R is actually, this I and R is actually the angle that you are concerned. Okay, so now, okay, let's look at the first part. Okay, explain why the light ray will not travel through the original direction. This one is, I would say, you will see this question quite often in various style. Okay, primary examples that they will ask you explain why the light ray change direction. How did the light ray change direction? How did the light ray change direction upon exiting certain medium or entering certain medium? Or how explain why the light ray actually bend towards normal or bend away from normal? Please explain. So these are the different style of questions, but primarily they still deal with the same concept, whereby when the speed of light crosses different medium, okay, the speed of light will actually changes. Okay, because of this change in speed, it will actually result in this change in directions. So for example, in your keywords, you will tell me that the speed of the light actually decreases as it enter different medium. What medium you must highlight. So my air will be less dense, medium. My glass will be my optically dense medium. Okay, so you must know where the light transverse or where the light ray is going. So upon this change in speed, upon crossing this different medium, this will result in the light ray bending. You must tell me whether it bend towards normal or bend away from normal. So these are the 3 keywords I'm looking for. Every time when you look at light ray, when they talk about how light travels, how light behave across different medium, the 3 particular keywords that keep appearing in all answers is, firstly, the students must tell me what happened to the speed, and the student must account for this speed change because of the crossing of different medium, from what medium to another medium. Then the third one is you must tell me what is the particular outcome, whether because of the change in speed when it crosses different medium, whether the ray will bend towards normal or bend away from normal. So in this answer, you actually have these 3 particular keywords. For 5B, I would say it's quite straightforward. Once you know it is optically denser, it bend towards normal, I would say 5B is quite straightforward. We just need to account for different path or different point of contact. In this question, the question says until it leaves the mirror. So what happened now is that you take a look, okay, when it enter the glass block from less dense to dense, from less dense to dense, it actually bend towards normal here. It keep traveling and you actually hit the reflecting surface. And reflecting surface means it will be reflected. So which means that this angle I'm looking for, angle of incident and angle of reflection should be the same. And from there, you continue on the ray with a refraction out of the glass block, or what we call refracted into the air itself, which is what we know as your bend away from the normal here. So eventually the path of the light ray until it leaves the mirror would look something like this on the screen. Part C is the basic use of refracting index. Okay, the Snell's law, the formula. Okay, whenever the question gives angles, and this angle may not be the angle of incident that you need. Always remember, for light ray, angle I'm looking at is always angle measured from the normal. Yeah, not from the surfaces. Because based on the question, the angle is 50. So that's why you need to 90 minus 50. So this is what we know as your angle I. Where the angle I. Just substitute the formula into Snell's law and you should get the answer. Snell's law, okay, I always like to write Snell's law this way. Okay, the Snell's law, this is the refracting index of the dense medium. So the formula will actually be sine, okay, angle in the less dense medium divided by the sine angle in the dense medium. So in this way, I will know which angle am I looking for. If I know is the angle is in the less dense medium, I will know it's at the numerator. If the angle is at the denser medium, I actually will park it at the denominator. Another word of caution is that when you're looking at Snell's law, sine or cosine, remember to change your calculator to degree modes. Okay, somehow we actually take AMAth and we actually leave, and AMAth uses radian modes, and we actually leave our calculator in radian mode. If it's in radian modes, the sine and cosine, the trigonometry will be affected in the number. So remember, after the AMF paper, before the physics paper, do a reset on your calculator, or actually just set your calculator back to degree modes. Okay, just take note of this. Small subtle mistakes. Okay. Then of course the question asks for the angle made by the light with surface AB. So remember, okay, so with the calculation, the question doesn't want angle R. The question actually want this angle. This is your angle Y. This is the answer. Okay, this is the answer that I'm looking for. Right, so that's why eventually once you get 25.4, this is the angle of refraction, yes, but this is not the angle I'm looking for. Right, so that's why you have to do a minus 90 degree to get the complementary angle, which is 64.6. Question 6. Okay, question 6. Question 6 is a transverse wave, or what I call it, EM wave segment, where we utilize EF V equal F lambda. Question 6 is one of the, I would say, the most straightforward question. Okay, whereby you just put a formula and it works really. Okay, so but question 6 is straightforward, yes, but 6B is also straightforward. It's quite a common question when you look at sound. Particularly when the question always asks, how does sound travel from one place to another place, or how is sound produced? Or sometimes they will say how is sound being transmitted, or how is sound travel through water? So whenever you encounter this type of question style, all these style actually looking at the same answer technique. In a sense that your answer will actually encompass of two but important keywords. Firstly, it will actually include the definition of the longitudinal wave. So whenever the questions talk about how sound is produced, the first line I will always end up is I will quote the definition of longitudinal wave, which means I will actually tell the marker saying that when sound is produced, your particle will actually vibrate parallel. Remember, a particle will vibrate. This is tagging keyword, parallel to the wave motion, or sometimes we call this the wave travel. Okay, so remember the tagging keyword, wave travel. This is the tagging keyword, particle vibrates. So when you talk about definition of longitudinal wave, of course, compare this to perpendicular transverse wave, is the use of the word parallel instead of perpendicular. But same thing, the tagging keyword I'm looking for is actually particle must vibrate. Okay, so these are the tagging keywords that you may want to pay attention with. Okay. Now, then the second set of keywords that I'm looking for is actually this statement here. You will set up a series of refraction and compression in the air itself. Because as we all know, is that actually sound is actually consists of refraction, series of refraction and compression arranged differently to make up different syllables. So if you look at your keywords, the second keywords I'm looking out for is to tell the marker to say that a series of repetitive pattern is being produced, is being set up. What repetitive pattern I'm looking at is particularly refraction and compression. Remember, when we're looking at how sound is produced, how I hear a sound, how sound travel from A to point B, the answer is actually quite standard one. You start with the definition of longitudinal wave, and you remember to, after that you follow it through with a statement to say that the pattern, the series of refraction and compression is actually being set up. So I would say that this is quite a standard questions that most examiners actually like to ask. Okay, so it's good to take note of. Part C, speed of sound in vacuum is 330. 330 is correct, but speed of sound here with 330 is speed of sound in air. Okay, not vacuum. Remember, sound need particles. For you to set a series of refraction and compression, I need particles. And if I need particles, means it has to be the medium. Meaning it has to be solid, liquid, or gases. Okay, so the medium has to be in this stream medium. It cannot be vacuum because vacuum has no particles at all. So in vacuum, speed of sound is actually 0. Okay, so just take note of this. Question 7 actually look at electrostatics. Look at drawing electric field pattern. Whether it's electric field patterns or magnetic field patterns, the standard field patterns, students are actually required to know them. Okay, to know how to draw them correctly. Okay, so this one I won't go through much. Actually, the answer is exactly in the same in your textbook also. Now, one of the I would say it's a unique question, but not commonly asked, is how do I determine the electric field? The other variation of this is how do I determine the direction of magnetic field? So both answers, okay, as a students you may want to look up to see what are the correct way of writing it. In this case, for electric field, the easiest one is the only way that we look at it, what's shown in the textbook is actually I uses small positive charge. Okay, so by convention, we use a positive charge. I drop it inside the electric field, and what I do, I observe where this positive charge move. Okay, so where this electric charge move, it will actually dictates or it will actually indicates the direction of the electric force acting on the charge. And as a result, it will give rise to what we know as your electric field. So for example, in this case, if I put a positive test charge here, and the positive test charge move towards my left-hand side, okay, this is the direction. So it will imply that the electric field is usually in this direction, okay, and is denoted by this arrow here. So the direction will be denoted by the positive test charge. Okay, so by convention, this is how we test positive charge. So, but what importantly is that the students have to say that the use of a small positive test charge. We don't write negative electrons or anything. You have used small positive test charge. And of course, inherently, your statement, you must tell me that the direction of motion actually give rise to the direction of electric field. Okay, and this is what is essentially what the question is actually asking for, to describe the direction of electric fields. The rest, part B, I would say the calculation, we just employ the few of the formulas, which I equal to QT. Okay, these are the small circuit formula that you need to remember. E equal to V over VQ, or what we call potential difference equal to energy divided by charge. So this formula, I would say most students, you should actually take note of it. But one thing I need to highlight to you is one of the small careless mistake we might make. Okay, is the use of the prefixes milli. So because the question say milli, remember is times 10 to the power minus 3. So if you use milli in your formula, you must remember to convert it to your SI and the SI unit. So if you use T, especially in the formula T here, remember to convert it to 1.2 seconds. So which the full number should be 1.5 times 10 to the power negative 3. Okay, so the prefixes, remember to utilize it. Okay, don't just put the M there and forget about it. Question 8, circuit. Look at 3 resistors. Okay, arrange 2 in parallel and 1 in series with another. Okay, the first question here, part A, you look to identify the cross-sectional area of the wire used. Now, first thing first is the use of this formula, rho L over A. I would say for this particular question, if I use this formula, okay, they will come in 2 different styles. First one is direct substitution. Direct substitution, which means I give you resistivity, I give you length, I give you area, I ask you to substitute in. Of course, this includes converting the unit so that the units all tally. For example, length must be meter, area must be meter square, all these things. So the first style is substitution, direct substitution. You just substitute all the number in, press your calculator, you get the answer. That's the first version. Second version actually includes comparison, whereby it's the same as what is mentioned here, whereby I give you actually 3 different wires, 3 different resistors. Okay, 3 different resistors, and they have different characteristics. Two different resistors, and they have 2 different characteristics, or they have some common characteristic between the 2 of them. Now, for example, for 3 ohm resistor, you actually have a length of 50 cm and a cross-sectional area of 1 times 10 to the power minus 4 meters square. For 4 ohm resistor, you actually 100 cm. Okay, and one information that we tend to miss out is actually the first line. The 3 and 4 ohm resistor are actually made of the same material, which means that these two, the resistivity of 4 ohm of the 3 ohm resistor and the resistivity of the 4 ohm resistor, they are actually the same. Okay, so this in fact is one of the most important, like the starting point to solve these calculations. Okay, so for determine the 4 ohm resistor, this is what I mean by the second style when I'm looking at this formula. They ask you to compare. Okay, so I compare 3 ohm and 4 ohm. So what do? I look for the common factor between them. And the common factor is actually resistivity. They have the same resistivity. So what I'm looking for is actually this. And so this is actually rho 3 equal to rho 4. The resistivity of 3 ohm resistor and the 4 ohm resistor is actually the same. And with this in mind, immediately I will not make R the subject. I will actually make resistivity the subject, which is RA over L. Okay, so if you do this, you will have actually what I'll write here. This is what I will have R3, okay, A3, okay, resistor of A3, area of A3, and the length of A3, and length of 3 ohm resistor equal to the resistor of 4 ohm, area of 4 ohm, divided by length of 4 ohm resistor. So by characteristic comparison, you look at, because since both of them have the same resistivity. Okay, so the ratio must tally. So once you have the breakdown of the mathematics, for example, this, okay, all you that need you to do is actually to substitute them into the right formula, right value, sorry. So once I have this, I substitute them into the right values, and I will actually solve for my unknown. In this case, my unknown will be A4, okay, cross-sectional area of the 4 ohm wires, and with that, the answer actually will come out quite easily. In fact, okay, 1.5 times 10 power minus 4. Okay, so this is how we look at, if you look at the calculation for resistivities that involve calculation of resistors. Next will be the resistors, effective resistance of the three resistor. You should know that the 4 ohm resistor are actually in parallel first. So these 4 ohm resistors are 100% parallel each other. They are not ambiguous. So yeah, they are neither series nor parallel. So it's very sure, I'm 100% sure they are in 4 ohm, they are in parallel. So I will sum them immediately using the formula for parallels. Parallel. So remember, for parallel resistor, it will be R parallel, we go to 1 over R1 plus 1 over R2. Okay, so this is the first formula I use to sum up the resistor is parallel. Then what I do is I will add my 3 ohm, because the parallel resistance will actually be in series with my 3 ohm resistor. So that's why I'll add them together. Okay, so that's how I get the formula here. So eventually the answer will be 5 ohms. 3C, okay, 3C, 3C and 3D, I will not go through much, okay, because I would say it's quite a standard question for circuit. Section B, for 9A is I would say it's about how sound travel. The first thing is how pulse of sound return to the ship. It's actually through simple reflection. Okay, upon hitting the surfaces, okay, the object will actually be, the sound will actually be reflected. For echolocation, remember, very often the question will actually give you the time to go down this way. So this is what you know, the distance D. And in fact, sometimes when they give you distance D, they will also give you the time taken to actually travel down this way. I'll call this time 1, and actually the distance time D1. Okay, sometimes it's one way, but sometimes the question will tell you the distance or the time taken to travel two-way. So sometimes the question, instead of giving you one way, the question will actually give you two-way. So go down, come up. Okay, so this is the time taken. So just take note, if you look at sound, because it's traveling at constant speed, we are looking at distance divided by time for speed. But take note, if the time is only one way, which is the red color one, T1, so the speed of the wave itself will be distance 1 divided by T1. Okay, but if the question given the time, the green color one, okay, it's a T, okay, so it's two-way, go down and up. Okay, so in this case, if I want to calculate the speed, it will be the same answer as previously, D1 divided by T2, but the formula is different. Okay, so the distance given will be the time taken for 2 trips. So the distance will be 2 trips also. So distance will be down 1 time, D1, then after that up another time. So in fact, your numerator distance actually is two-way. So that's why there's a 2 times D1. Because the time given to you is actually two-way. Go down and come back. But the answer will be the same. Both S, speed of sound, is actually the same answer because they are in the same medium. Okay, so just take note of this subtle difference. And if you take note of this, actually you have done, like, question B shouldn't be a problem. Same as before, question B, if you look at calculation, there are standard traps, standard booby trap that the examiner try to block you. Okay, remember, if you look at prefixes, if I use prefixes, milli, remember, please convert the milli back to your zeros. Okay, milli is divided by 1000, so 100 milliseconds is actually 0.1 second. So remember to convert the milliseconds back to SI unit before you use it. Okay, so just take note of it. Part C, I would say there are two. The marker give 2 answers which are actually fairly good. Okay, state one reason why the answer in B is always an approximate value. Other than this three, okay, the one possibility is that the C bed may not be smooth, because what happens is that you may have a jagged edge C bed. So the C bed will be jagged, and because of jagged, the C bed height or depth will be uneven. Okay, and because it's uneven, that's why if you measure it at this particular location, and maybe you measure at this particular location, the C bed, there will be a slight differences, okay, because of the jaggedness. The other possible reason is that the pulse emitted may not be vertically downwards. Yeah, true enough, because your boat is actually rocking in the sea. In actual fact, the boat is actually going up and down by the wave. So it could be a time whereby instead of pointing the sonar downwards, it may be like a bit slanted this way. So maybe the path is a bit slanted this way. Okay, so the time taken up and down, the path traveled may be a bit longer than usual. Right, so if it's vertically down versus slanted, the path taken will be longer, and the path taken, if it's longer, means the time measured or recorded will actually be longer. So the time will actually be not the exact timing. Right, so two possible reasons that as in why the depth of the bed may not be the same, or maybe just an approximate value. The rest, part D, part D, I would say quite straightforward. Now, same thing. For part D, part 2, how sounds travel. How sounds travel is the same as light. How light travel through different medium. There are standard keywords that the marker is looking out for. In this case, we look at sound. How sound travel, there are standard sets of keywords whereby you deal with like definition of longitudinal wave, and you look at the series of refraction, use of series of refraction keywords. Now, but pertaining to reflection, how sounds changes. Okay, pertaining to reflection, there are also a standard set of keywords that you want to take notes. Okay, so when you talk about the standard keywords, okay, you have to take note is that when for this question is about from water to solids. Okay, when the question say the pulse strike the seabed, okay, it part of the wave actually travel through the seabed. The seabed is what we know as your solids. Okay, so previously it was in the seabed. The sea is before traveling the seabed, it's actually traveling through the sea, which is the water, which is liquid. Okay, so it's traveling from liquid to solid, and we all know that for sound, okay, from liquid to solid being densely packed, closely packed, okay, the speed of sound will actually increase. Right, so the speed of sound will increase when it enter the solid medium. And why is it so? It's like what I mentioned before, because solid is a denser medium and the particles are closely packed. Remember, for sound, transmission of sound, it requires the sound particle to set up a series of refraction and compression. So the closer you are, the faster you are able to do this. You are able to set up this, and the faster you are able to transmit the sound. So as a result, because solid are closely packed, more closely packed than liquid and gas, the transmission is actually much, much faster. So that's why for speed of sound in air is actually one of the slowest, and in fact in solid, the speed of sound in solid is actually one of the fastest. Right, so you look at the keywords we are looking at. For this particular keyword, I'm looking at the students being able to identify the changes in speed, and the students are able to relate the molecular structure or the closely packed density with speed of sound itself. Okay, so that's why these are the two keywords that I usually look at when I look at how sound changes pertaining to reflection. Usually, I always remind students is F net equal to ma, net force acting on object. Okay, so now the ship okay, is actually on the boat itself. Okay, so there's a forward force of 2.5 times 10 to the power 5 Newton, and there is actually a resistive force, okay, which is backwards, the water resistance, okay, which is given by the question 1.2 times 10 to the power 5. So if you look at the forces, since there are two forces acting on the body itself, the net force will actually be difference between these two. And the mass is given, okay, and you substitute all the formulas, you will find that the answer for acceleration will appear quite easily. Nothing fanciful here. It will be a standard dynamic question. The common one that we look at is terminal velocity. Okay, when the resistance actually increases. Okay, the most common way that you see this particular scenario is when I drop the ball. When I drop the ball from air, as the ball go faster, the resistance actually increases. So instead of using water resistance, the common question will be air resistance. I drop the ball down. But the situation is actually the same. As the object move faster, the air resistance will actually increases. Okay, air resistance is proportional to the speed. Okay, so the faster I move, the higher is the resistance. And true enough, when the resistance increase, okay, here the assumption is that the forward force is the same, the applied force is the same. But applied force is the same, meaning the highlighted one, this applied force remains the same. Okay. On the other hand, my resistance force is actually getting increasing. It's getting higher and higher. So my backward motion, my backward force is actually getting increase and increase. It's getting higher and higher. And what's the impact? Is that the net force applied on the object will actually be reducing. So when I net force reduce, my acceleration will reduce. Okay, but remember, decreasing acceleration is still means that the object actually the velocity will increase. So this is what happens to the initial phase. And same thing when my velocity increases. When my velocity increases, based on what the question says, the speed increases, the resistance increase. So which means my resisting force, my R, will actually keep increasing. And eventually, my net force actually will end up to be 0. So when my net force is 0, my acceleration will decrease to 0. Okay, so this is one of the classic examples when you look at terminal velocity, when you look at how object behave, how the speed of the object or how the acceleration of the object changes when it's being dropped from a high location. But now for this water, instead of dropping from high location, we are looking at the horizontal motion. But the concept of it is still the same. We are looking at how it reaches terminal velocity. So the keywords that encompass is always the same. The students need to look at the usage. The student need to highlight to the marker what happened to resistance, what happened to the net force, and eventually tie in to what happens to the accelerations. Okay, so these are 3 keywords that we always remind students to write when they pertaining to terminal velocity. So now let's look at the next question. Question 10. Look at vector additions or sum of forces. For science physics, for this year, okay, the new syllabus, this particular topic for summing of forces, this particular concept is not in syllabus. Okay, for the previous years, yes. Okay. So for this new syllabus, this particular question is not in syllabus. Now for part C is pertaining to kinetic energy. It's a very straightforward energy. It's a straightforward case whereby you look at the conversion for part 2, you look at the conversion whereby you look at energy in potential store being converted to energy in kinetic store. And when I do this, okay, I will actually look at the formula for kinetic energy, which is half mv squared. Energy in gravitational potential store, which is mgh. And since there's no losses, okay, the energy is conserved. It will be equal sign. And from here, I will be able to find what is the velocity that I need, okay, through some manipulation of algebras. Now, for this question, I'm actually more concerned about C part 1, whereby the question asks students to state what is principle of conservation of energy. For this particular question, this type of question, from my experience is that the students always will remember to write the first segment. And very often, most of the students actually will forget to write the second statement, which is total energy remain constant, and it has to be in the isolated system. For conservation energy to be true, for it to be used, okay, there are certain conditions that the students must take note. Is that energy cannot be destroyed nor created. That's first thing. And it also says that the system has to be an isolated system, and because of the isolated system, the total energy in the system actually remain constant. So these 2 conditions or these 2 statements actually is what make up principle of conservation of energy. So when the marker asks to state the principle of conservation of energy, it's utmost important to actually know these 2 conditions. It has to be stated, not either one. Okay, so just to take note is for 11 DC motor. Okay, DC motor here. I would say it's a classic question for DC motor, but what's of interest to us, okay, is actually part C. Okay, so we will do it step by step. Now, for part A is a DC motor rotating, and for DC motor to rotate, we know that there has to be an external power source. Okay, so for the external power source, is given by the picture at the bottom, and it's actually governed by 3 color code wire. Okay, and the wire is actually given here. So now, I would say that most of us have no problem with identifying wire C as being the earth wire. Okay, because it's connected to the metal casing. Okay, remember, earth wire is actually connected to the metal casing. But what maybe some of you tend to leave out, forgot, is like how to identify the live wire and neutral wire. So the common definition for live wire, you must remember, is that live wire is denoted by the current carrying the wire that carry current away from the sources. So if the current come out from the sources, in this case, that wire B is considered as live wire. So wire B will be your live wire. And similarly, how do I consider that wire to be a neutral wire? By definition, a neutral wire is the wire that carries current back to the power source. So I carry the current back to the power source. So in this case, wire A is actually what we know as the neutral wire. So in this case, I would say it's the way we define. Okay, but in real life, wire A and wire B, live and neutral, they are actually the same type of wire. But what differentiate wire A, wire B, the live wire, and wire A, the neutral wire, is that the current is carrying the current flow. Okay, always remember current carrying from the source is actually known as the live wire. Wire that carry current back to the source or back to the source is known as the neutral wire. And from there, you will know the respective color lah. Part B, how does the fuse works? Now, when we talk about fuses, we look at the 6 precaution method that we look at. We have your earth wire, you have your you have a earth wire, you have your fuse, you have your socket, you have your you have your circuit breaker. Then after you have your double insulations. Then after that and last one is your switches. Okay, so now these 6 precautions, okay, they have their standard keywords. Okay, so as a student, you must know how to use them correctly. For example, what we are looking at is fuse. Fuse, one of the keywords that we look at are the one that is underlined. How or when is fuse activated? Okay, fuse is activated when the current is high. How high is high? Okay, so definition of high, when we look at fuse, is the current has to be higher than the fuse rating. So this is one keyword that I always ask students to remind students to write. What happens when the current is higher than the rating and flow in the wire? The fuse will melt. And what's the importance of the fuse? What's the purpose of the fuse? It's actually when it melts, it will actually disconnect the appliances from high voltage. And what happens? No current will flow. And this is how fuse actually protect the appliances. Where the moment it detects a current, what current we are looking at? Higher than the rating. Then the fuse will start to melt. And once melted, it will what's the implication? It will actually disconnect the appliances from high voltage, prevent current from flowing through. And with this, it helps to protect the appliances from burnout or from catching fire. Okay, so these are what I mean by the keywords for each of the precautions. Okay, the keywords for this precaution, I actually have them in my playlist. So take note, okay, you can refer them to the top. Okay, I actually link it up on top. So you actually can take a look at the playlist for under practical electricity to look at the keywords. Right, so you may want to revise them. Okay, if you forgot about them, if you have not done them, okay, it's time to go and take a look before the exam so that you actually are well prepared for this particular topic. Because the 6 precautionary methods are actually quite popular type of questions if you talk practical electricity. Part C, okay, explain in terms of magnetic fields, how does the current in the coil of the motor produce the force? Okay, here the questions is not asking for Fleming left-hand rule, where to pertaining to induced force acting on the coil itself. But indirectly, the question is looking at the use of magnetic field lines. Okay, so now how we are looking at is this. Let's say I draw a side view here. So this is the north, this is the south. Okay, so now we look at the wire one by one first. Okay, so now I look at the wire on the left-hand side. So now let's look at this. Okay, wire on the left. So I denote it by it's flowing out of the paper. So it will denote by a dot here. So this is the current. So if you look at the current itself, okay, if you look at the current itself and you look at the magnet itself, both of them will have magnetic field lines. Because based on what Maxwell stated is that if I have current carrying conductor, I will actually generate my own magnetic field lines. If I have a magnet, I definitely have magnetic field lines. So for the magnet itself, the field line is actually from left to right. Okay, from my north pole to my wrong color. From my north pole to my south pole. So in this case, it will be this way. Left to right, left to right. On the other hand, for my wire, if I use Maxwell's right-hand rule, I will find that my field line, okay, will actually be in the anti-clockwise direction. So my field line will actually be this way. Okay, so this will be my field line. Okay, so you have my field line. Okay, it's hard to draw here. Okay, and in this direction, you look at direction, it's anti-clockwise, so which means the bottom side is going to the right, the top side is actually going to the left. All right, so in this case, you take a look. If you look at the direction of the magnetic field line, you'll find that the top side, okay, for the current, the field line is going to the left. The top side, the magnetic field line for the magnet is actually going to the right. So you'll find that for the top side, these two magnetic field lines, the red and the blue, the field line by the wire and the field line by the magnetic is actually in opposite direction. So I would say that the top, because of they are in opposing direction, this magnetic field line will tend to get smaller. Because they are in the opposite direction, they'll cancel out each other or they will make it smaller. So actually the top side is actually weaker. And on the other hand, you look at the bottom side, okay, the bottom of this cable, you'll find at the bottom of the cable, the red color one, the field line is actually on the from left to right. Okay, the red color one. And at the same time, the field line by the magnet is actually left to right also. So you'll find that if you consider the bottom of the wire, the field line at the bottom of the wire, they are both in the same direction. So if in the same direction, these two field lines will actually reinforce each other, making the field line at the bottom to be actually stronger. So what does this mean is that you will have two section here. Example, using the wire as a center. I'll have the top side. Okay, this side, the magnetic field line is actually weaker. And I will have actually the bottom side here. Okay. The bottom side here, because the field line actually reinforce each other. The red and the black, they reinforce each other, they make it stronger. So I actually have a field line that is actually stronger at the bottom. And because now I have a difference in the magnitude of it, difference in the strength of the magnetic field line. So you find that I have a stronger magnetic field line at the bottom, a weaker magnetic field line at the top. And when I have a difference in the strength, I will actually have a force being exerted. And where is that force being exerted? It's always in the direction of strong magnetic field line to the weak magnetic field line. So that's why I will know that a force will be exerted in the upward direction, okay, from the strong field line to the weak field line. And when the force is exerted from the bottom up, it will actually push the wire, okay, in a clockwise direction. This is what I mean by clockwise direction this way. So the rotation of the field line, the rotation of the coil is actually due to the difference in the magnetic field strength on the top side of the wire and the bottom side of the wire. Okay, so if you look at this particular side of the wire, you'll find that if I'm looking at this side of the wire, the left-hand side of the wire here, okay, you'll find that the induced force will actually be exerted onto the wire upwards. And if you do it for the opposite wire, the opposite side, where you'll find that the force induced will actually be pushing downwards. Right? That's why the coil itself actually will rotate and will rotate clockwise. And this is what the question is asking for. Of course, you don't need to write in so detail because the question is asking only for 2 marks. For 2 marks is just for a simple explanation of using magnetic field lines. So the important things that you need to tell the marker is that the use of the magnetic field lines is that the coil field line, the current field line in the current will actually interact with the magnetic field line. So you are looking at 2 different field lines interacting together. Okay, and this field lines is actually denoted by the top section and the bottom section. There is a difference in the strength of the magnetic field lines. And because of the difference in magnetic field line, the strength of the magnetic field line, a force will be induced on the particular coil itself. And this explanation actually ties in well with what Maxwell has said. You are able to use Maxwell difference in magnetic field strength to actually explain the force induced. Okay, so for part C, this is the question that you need to take note for this particular segment here. Okay, now, part D is a standard calculation for power. Yeah, so it's it talk about useful power and non-useful power. So I would say it will straightforward question here where we look at the power related IV, and from there, why? Because the question actually asks for the power loss. It will give you the power loss. So you'll be able to find what is the useful power. P equal IV in this question here, we'll actually look at the total output of the total power of the motor itself. Okay, for part D1 and D2, T1 is not a big issue. D2 also actually not much issue except for some conversion. Okay, now when we look at kilowatt hour, okay, part 2 is just to take note, whenever we use kilowatt hour, okay, energy, we all know that the formula is energy is power times time. Okay, and we are very comfortable with using SI unit. Okay, we have to use SI unit in most of the formula. But for this case, because now we specifically says energy has to be marked as kilowatt hour. Remember, the SI unit for energy is actually is actually in joules, not kilowatt hour. But now I purposely pack it to kilowatt hour. So which means my power and time, it cannot follow SI unit. So whenever we calculate energy in terms of kilowatt hour. When do we use it? Cost of electricity. So whenever we find cost of electricity, we definitely need energy to be in kilowatt hour. And when we need energy in kilowatt hour, I need power to be in the unit kilowatt. I need time to be in the unit of hour. So when the question say half 30 minutes, okay, we must remember to convert the time to hour, which is half an hour. When the question says the power is 200 watts, okay, the power is 200 watts. Okay, I cannot just use 200 watts. I need to convert it to kilowatts hour. So that's why I need to divide by 1000. Remember, 1 kilowatt is 1000 watts. Okay, so you must remember to convert. So for calculation of electricity, especially when calculation of electricity is straightforward, but just that there are small subtle changes, especially when you deal with kilowatt hour. So remember, energy has to be in kilowatt and the time needed has to be in hour. Okay, so just to take note of the small calculation. All right. So with this, we come to the end of the paper 2 here. Okay, so if you have not done your paper 1, you can refer to the video for your paper 1, okay, which is in the next video. Okay, on that, okay, remember, okay, if any questions for this particular paper, leave a question in the comment bar below and just so that I will take note and I will get back to you ASAP. Okay, now we have come to the end of the video. I hope the video has been useful for you. Now, the subsequent week, I will be uploading videos on certain chapters or on certain concepts that my students are asking. So if you want to get notification of these videos, okay, remember to subscribe to my channel and remember to press or to activate the bell button so that you will get notified the moment I uploaded the video. And I hope the video that I uploaded to you will be useful for you also. Okay, now, without delaying, okay, this is where I end off. Okay, I hope to see you soon. Bye-bye.